Good afternoon, everyone. Thank you all for being here and participating in today's IFPU Gravity webinar. Today we have with us Alberto Sesana. Alberto is currently Associate Professor at University of Milan-Bicocca. Alberto has vast experience in physics and astrophysics of massive black holes and gravitational waves, as seen in the numerous citations and articles published in the prestigious scientific journals. Through his academic career, he has been dedicated to the study of different topics, for instance, gravitational wave of astrophysical detection with laser interferometer and pulsar timing arrays, massive black holes, formation evolution, dynamics and observational signatures, stellar dynamics, dense stellar system, hypervelocity of star and the nature of the environment of Sagittarius A star, gas dynamics and accretion theory, structure formation, and galaxy evolution. Alberto got his PhD in physics from the University in Serbia in 2007. Afterward, he then moved to Birmingham for a short postdoctoral position in 2007 before spending 2 years in the USA at Penn State as postdoctoral scholar. From 2009 to 2014, he was first junior, then senior scientist at the Max Planck Institute in Potsdam, and in 2014 he was awarded the prestigious University Research Fellowship of the Royal Society, moving to the University of Birmingham. Since 2019, he was granted with an IRC and started his research group as associate professor at the University of Milan-Bicocca. Today, Alberto will talk about supermassive black hole astrophysics with pulsar time array. Thanks, Alberto. Go ahead.
Yeah, thanks for the introduction, man. That makes me feel so old. So thanks. First of all, thanks for the kind invitation, and of course, it's a pity to do this in. Well, it's good to do it in streaming because I guess more people can participate. But of course, it would have been nice to visit you in Trieste. And right, so I think you hit the jackpot in a sense because Enrico asked me to talk about astrophysics with pulsar timing arrays, and perhaps we are entering a very interesting time in this subject. And in fact, there's been an interesting paper that hit the archive right this morning, and I had to rush a little bit to include some of the results of that paper in this presentation. So, hopefully I won't go too long. But so here is my plan, which is to talk to you about pulsars as ultra-precise clocks that are useful for detecting gravitational waves. Then we talk a little bit about the sources that we want to detect with this technique, which are the primary source are supermassive black hole binaries. And then I will give you an idea of how you do that and what is the current state of the art, including these new results that came up today. Okay, so let's start. Well, I guess this audience, I don't have to explain what pulsars are and what in particular millisecond pulsars are. But for the purpose of this talk, pulsars are essentially lighthouses. Okay, you have this beam of radiation that, if intercepts the direction to the Earth, essentially produces this lighthouse effect. And since those are, spheres with a huge moment of inertia, it's very hard to change the spin rotation. So essentially, what you have is almost a perfect clock. Okay. In particular, so this is the famous PP dot diagram for pulsars. In particular, there is a subclass of pulsars, which are the so-called millisecond pulsars, that are especially good clocks because, well, you can see that heuristically, right? They rotate very fast, so they have a very short period. So the precision of their period, of which you can time their period, is proportionally precise to the period itself. Okay, so millisecond pulsars are essentially the best cosmic clocks that we can find in the universe. Okay, And what do you do when you have a clock? Well, you use it to measure time. And essentially, what people have been doing for 50 years, essentially, from the discovery of pulsars, is to record the time of arrival of those pulsars. So you see here an example of actually a normal pulsar. It is not a millisecond pulsar. So essentially, each time, at each rotation, you have this blip, okay? And you see these blips are very regular because they trace the rotation period of the pulsar. So what do you do? Well, you have a time series, okay? Then you have a model to describe your clock. So this is, for example, a rotator which has a period. It has a period derivative and a second period derivative. Perhaps it is in a binary, so you have all the correction due to the binary motion. And then you fit for the best model that you have. And then you compare the time of arrival of your fit with the time of arrival of your, the time of arrival predicted by your model with the time of arrival that you actually measure. And what you're left with is a residual, which is the difference between these two. And obviously these residuals are, have all sorts of origins because why they're there? Because of course there is errors in your measurement due to the fact that those pulses, for example, travel in the stellar medium. So there's scattering and delays due to the interstellar medium. The pulsars themselves are not exactly perfect clocks because there are all sorts of interesting physics that goes on in the pulsar crust or in the inside of the pulsar, most of which is actually unknown. Plus, obviously, you have your, okay, I didn't mention, of course, you measure the pulse of arrival, the time of arrival of these pulsars with huge, big radio telescopes. And you have, of course, errors in your measurements. Your system have intrinsic noise, and there is like the radiometer noise of your radio telescopes, okay? So essentially, the residual is everything is left when you subtract your model from your observations. So why this is interesting? Well, this is interesting because suppose now that you have a gravitational waves passing, intercepting the line of sight between the Earth and the pulsar. So the gravitational wave changes the metric of the space-time between you and the pulsar. So it changes the null geodesic that the photons travel, okay? And this change of the null geodesic is, produces essentially dephasing of the arrival of the pulse that is proportional to the amplitude. H is the strain, the amplitude of the wave. And essentially the residual that you measure, if you observe for a time t, where t is, a certain number of years, the residual at a given time is the integral between the start of your observation and that time of, this dephasing, okay? And since a gravitational wave is a sinusoidal wave, essentially, and you're doing an integral of a sinusoid, the amplitude of this residual is of the order of the amplitude of the wave divided by omega, okay? And if you do some math and you put, let's say you consider a supermassive black hole binary of 1 billion solar mass in the relatively nearby universe at a frequency of few nanohertz, because and this is because essentially with this technique, you can probe very low frequencies. And the reason is as follows. So essentially you are timing pulsars for, I don't know, let's say 10 years, and you don't time them continuously. You just go back to each pulsar, individual pulsar once a week or once a month, okay? So essentially the frequency windows that you can probe is 1 over the observation time, which is 1 over a few years, and 1 over the sampling rate of your pulsar, which is 1 over a few weeks. So the frequency range to which you're sensitive to is of the order of few nanohertz to few hundreds of nanohertz, okay? But you see that this number here is of the order of 10, perhaps 100 nanoseconds. And this is extremely interesting because we have now the capabilities of timing millisecond pulsars with this type of precision, okay? So potentially, millisecond pulsars are detectors of low frequency gravitational waves. So just to put this in context, let me show what I call the binary gravitational wave landscape. You should be familiar with this type of plots. So you have frequency of the wave on the x-axis and characteristic amplitude on the y-axis. So you all know about the ground-based interferometers like Virgo, and that detected gravitational waves for more than 5 years now, or perhaps 5 years, and that led to a lot of discoveries already. But with these interferometers, we are observing stellar mass objects. Okay, perhaps up to hundreds of solar masses, like the latest discovery that have been published. If you want to detect gravitational waves from bigger objects, you have to move to lower frequencies, and that's why we have. Okay, this is a old slide, so the small e here should go away. So we are planning to fly LISA, which is a laser interferometer that is going to open the gravitational wave window in the milliards regime, where we will be able to see a whole variety of sources, but in particular, merging supermassive black hole binaries. If you move to even lower frequency, and now you see that we are in the nanohertz regime. So what I sketch here is the typical sensitivity of a pulsar timing array. So you see, you have a window up there at these low frequencies. And what you're seeing there is actually the adiabatic spiral of the most massive black holes in the universe, okay? So this is essentially our target. Right, so why this is interesting? Right, because we know observationally that galaxies host supermassive black holes at their center. So every time we had the capabilities, we have the resolution to pierce into the center of a galaxy, we found a dark massive compact objects, which we will call supermassive black hole for convenience. And with the latest results of the Horizon Telescope, there is little room to play around, right? Either these things are supermassive black holes or are something very similar, okay? And we also know that these supermassive black holes are, present everywhere in the universe, and when they accrete matter, they shine as quasars. And we see these quasars already at redshift 7. So potentially we have supermassive black holes everywhere in the center of galaxies in the universe, okay? So we see these black holes in a lot of windows. We see them electromagnetically. So this is just it's a random compilation of pictures from the internet. So you see these black holes here accreting and shining as quasars, and you see these jets that are being emitting, prompted by the accretion onto the supermassive black holes. So we see them eating a lot of stuff, and we see them ejecting a lot of stuff. Okay, so those supermassive black holes do a lot of interesting things that we can probe already with electromagnetic probes or telescopes. However, we also know that galaxies merge pretty often in the universe, and in fact, our current understanding of the formation of galaxies is that it proceeds in a hierarchical fashion. So you see here what is called a merger tree, extracted from a now fairly old simulation from De Lucia et al. 2006. So what you see here is a cartoon of a very massive galaxy at time 0, and the breaking down of this galaxy into its progenitor back in time. Okay, so essentially galaxies start from small galaxies at high redshift, and these small galaxies accrete gas from the interstellar medium along filaments, and they merge with other galaxies to form the big galaxies that we see today. But we also know that the supermassive black holes that reside in the center of the galaxy, and you see here in the top right, the masses of these black holes correlate with the properties of the galaxies. So they correlate with the mass of the bulge, stellar bulge of the galaxy, and they correlate with the velocity dispersion of the galaxy itself. And this point toward the coevolution of the galaxies and the supermassive black holes. So the current model, how this correlation come about, is that in these proto-galaxies at high redshift, you seed black hole of a certain mass according to some mechanism which is largely unknown at the moment. And during a galaxy mergers, the two black holes migrate to the center of the merger remnant. They form a binary, and this binary coalesce through the emission of gravitational wave. And this process, gravitational instabilities feed gas to these massive black holes, and we see them shining as quasars. This is, of course, a very, very sketchy and simplified picture, but it gives you the idea of what is the main process. Okay, so a natural consequence of this model is that binaries of supermassive black hole inevitably form. Okay, however, we don't know much about these binaries. We don't know the nature of the seeds. We don't know exactly how they grow along the cosmic history, even though a lot of evidence has been collected through electromagnetic telescopes. And we don't know what is the merger rate of these supermassive black hole binaries and what is their effect on the cross galaxies and so on and so forth. So let me have a look at the journey of a galaxy following, of the supermassive black holes following a galaxy merger. So you see here on the top, 6 snapshots of a galaxy merger. Actually, those are obviously 6 snapshots of 6 different systems, because from the first snapshot to the last, it takes, you know, a giga-year or so, or maybe several giga-years, okay? So what happens when 2 galaxies merge? The 2 black holes, initially, they in spiral, they find themselves in the outskirt of the remnant galaxy, and they move toward the center independently because of dynamical friction. So dynamical friction is very efficient to bring the 2 black holes separately, let's say at the center of the galaxy, where they start to see each other, okay? At some point when the separation of the 2 holes is of the order of a few parsecs or a few tens of parsecs, depending on the mass and on the properties of the system, the 2 black holes bind into a binary, into a Keplerian binary, let's say, okay? And therefore, at that point, dynamical friction ceases to be efficient. On the other hand, if this binary becomes compact enough, gravitational wave emission takes over, leading to the coalescence of a binary in a short timescale. However, this timescale depends on the separation of the binary, and the efficiency of gravitational wave radiation is a very steep function of separation. So if the binaries are, for example, at a milliparsec separation, they would coalesce like in less than a million years, which, you know, on cosmic timescale is nothing. But if they are at a parsec separation, their mergent timescale, because of gravitational wave emission, is going to be longer than the Hubble time. So somehow you need the binary that is stuck here, because the dynamical friction is not efficient anymore, needs to bridge this gap and to shrink its separation because of some other physical process. And we have processes that do so. And these are related to the fact that the binary is not in vacuum, but it sits in the center of a galaxy in a very dense environment with a lot of stars and potentially gas. So I'm not going to spend a lot of time on this, but it has been shown through a lot of theoretical work, either using embodied simulations for stars or hydrodynamical simulations for gas, that interaction with the stars intersecting the orbit of the binary, or with the massive circumbinary disk, is able to extract efficiently energy and angular momentum from the binary, potentially bridging this gap and leading to the emission of gravitational wave and the final coalescence. Okay? So this is just a sketch of how this process happens. Now, obviously, one of the consequences of this picture is that there should be a lot of massive black hole binaries in the universe, but can we see them? The answer is yes and no, in the sense that depending on the scales we're looking at, we have different kind of evidence, of perhaps circumstantial evidence of the existence of these systems from electromagnetic observations. So here you see essentially this arrow from the top left to the bottom right is an arrow in separation. So it goes from, you know, tens of kiloparsecs down to 0. And depending on the separation that you're looking at, you have different clues of different evidence that there might be a binary system in that, a binary supermassive black hole in that system. So at very large separation, that's pretty obvious because we see double quasars, okay? So this is a pair of galaxies on the way to merger. The 2 black holes are lit by the inflow of gas, and they shine as quasars, okay? And this is the very early stage of this pairing process that I talked to you before. Let's skip some of the passages here. Just wanted to say that the secure evidence that we have for what is perhaps a binary system, but it's not clear, and I say, I specify that in a second, is this system here, is from Rodriguez et al. 2006. What you see here are two compact radio cores. And the projected separation of these two compact radio cores is 7 parsecs, okay? So those are two compact radio cores which are indicative of accretion onto a compact object. And so there are two massive black holes in this system. Now, why this is perhaps a pair, perhaps a binary, because we don't know exactly whether these two black holes feel each other's gravity, so they are already what we call a binary, or their dynamics is still dominated by the material that is within them, okay? But though this is I would say the most secure evidence of a closed pair of black holes that we have. Moving to a smaller separation, we have other pieces of evidence that come from spectral lines or from periodicity that are debatable, okay? These have been put forward as candidates, binaries, but we lack the smoking gun, okay? The idea, for example, for this periodicity would be that there is a binary, like you see here, accreting from a single binary disk. You have an obvious periodicity in the system, which is the period of the binary. And so you perhaps expect periodic accretion leading to periodic luminosity. But this isn't really a smoking gun. So those are tentative candidates. So I would say there is circumstantial evidence of the existence of these systems. And you expect to be so because, it's very, very hard to pin down a binary, which is like less than a parsec across at cosmological scales. So what this binary does in the gravitational wave band? So essentially, if you take a cartoon of a binary here, okay, during the inspiral phase, the binary emits essentially a sinusoidal wave, okay? And what you see is the superposition of these two contributions here, which are essentially the wave hitting the Earth and the wave hitting the pulsar. And what you see, the timing residual that you expect are essentially the blue curves here. And this is from a circular binary. And on the right, you see one from an eccentric binary, okay? So you're looking for a signature like this. You see, this is for a system that I just made up, and you see that the typical residual is 10 nanoseconds for these systems. You're looking for something like this into your timing data of your array of millisecond pulsars. So these are 17 millisecond pulsars from the Parkes pulsar timing arrays. It's not even that simple, because you don't have a supermassive black hole in the universe, but you have a population of inspiraling supermassive black holes that are all emitting at their gravitational wave. And if you just add up all their contribution, what you expect to see is essentially a stochastic background, which has a shape that is given by this simple equation here. You can essentially say that you expect a signal which has a spectrum that goes with the frequency to the -2/3, characterized by the given amplitude A. The assumption here is that these binaries are circular and are gravitational wave driven. In the bottom plot, you see a mock population of supermassive black hole binaries, and this is the population, the cosmic population that would contribute significantly to the signal in the pulsar timing band. So you see, we are talking about 10 to the 8, 10 to the 9 binaries, so the most massive binaries in the universe, at redshift perhaps as high as 1. So these pulsar timing arrays are totally complementary, for example, to LISA, which is sensitive to much lighter black holes and farther away in the universe, okay? So here you're really probing the beast in the, let's say, cosmological nearby universe, okay? So let me just dig a little bit more into this signal. How does it look like? So what I plot here is frequency against characteristic amplitude against frequency. Each triangle here is the signal from an individual binary, and the green line is the superposition of all of them. So you see that the low frequency, you sit onto this f to the -2/3 power law, okay? But at high frequency, signals become sparser and sparser, and you might have individual binaries that actually dominate the signal, okay? So what you expect to see is a mixture, is perhaps, it's a stochastic signal, but perhaps you see first the overall contribution of the stochastic background. Perhaps you're lucky and there is a very massive binary in the Virgo cluster, for example, and you might see the individual signal from those binaries. Now, if I take this signal and I inverse Fourier transform it into the time domain, what I get is the red line here. So these are two, let's say, synthetic data sets where I injected this population into some timing residual of the pulsars. And I superimpose to this some white noise, okay? And this is the green curve. So you see this pretty much look like this thing here. This is a random pulsar that I just took. So, you know, is this a gravitational wave background? Not so easy, right? Because pulsars do a lot of things that we don't understand. So it's really hard to say that there is a gravitational wave signal by looking at a single pulsar. That's why the way to do this is to actually put together an array of pulsar and build a pulsar timing array. Why this is crucial? Because since gravitational waves are quadrupolar, they imprint a very specific correlation pattern in the time of arrival of different pulsars, okay? And this correlation pattern goes like this. So this is the Helings and Downs curve from, you know, the two physicists that derived it first in 1983. And what you see here is the correlation that you expect in two time series from two pulsars as a function of the angle between those two pulsars. So the idea is to time as many pulsars as possible so that you can populate this correlation plot and eventually detect this correlation. So this Helings and Downs correlation among a vast population of pulsars is what is considered by the community the smoking gun of a gravitational wave signal in pulsar timing arrays. Now, obviously, you don't just plot, you know, points on the graph and say, oh, okay, this is a detection. There is a whole framework to do so, which is based on a likelihood function that essentially looks for the cross correlation of the correlated signals within the pulsar. So essentially what you do, you concatenate all the timing residuals of all your pulsars and you build this huge matrix, okay? And this provides the correlation matrix between your pulsars. And what you try to do, you try to detect in this correlation matrix, this pattern here, which is the mathematical formula of these Helings and Downs. And you do this with your, you know, super duper Bayesian code, including all sort of noises, et cetera, okay? Now, I don't have time to go into the details here, but this is a very, you know, sophisticated and complex framework that has to include all sort of sources of errors, uncertainties, and so on and so forth. I get back to that in a second. So just to give you an idea, suppose that we have a certain amount of pulsars, what you are, you know, the signal to noise ratio to which you detect this pattern here, essentially is given by this formula here, where you are summing all the Helings and Downs coefficients, which are these gamma functions here, in all your pairs of pulsars, okay? And that's why it is of paramount importance of having a lot of pulsars in your array. So you see this SNR goes linearly, in fact, with the number of pulsars that you have, and obviously increases with time, okay? And these graphs here essentially show how you expect this SNR to progress as you take more and more data. As long as the signal is small, compared to the noise of the pulsar, the increase is sharp. When the signal becomes comparable to the noise in the pulsar, this is the reason for this is because, you know, the stochastic background is in itself a source of noise. Okay, this SNR builds up much slower, and it becomes essentially proportional to the square root of time. Okay, so you know where you're hitting SNR1 or so, you are in this transitional regime, which is where you expect to start seeing something in your data. As I said, it's of paramount importance to use an array of pulsars to do this type of enterprise. And that's why people have organized, the scientific community has organized in the so-called pulsar timing arrays collaborations. We have 3 main collaborations worldwide. Oops, I have a telecom. One is the European pulsar timing array, making use of the 5 large European telescopes. We have NANOGrav in North America that is using Arecibo and Green Banks. And we have the Parkes pulsar timing array using the Parkes radio telescope in Australia. And these 3 pulsar timing arrays are joining force in what is known as the International Pulsar Timing Array. And the idea is, okay, the more pulsars we have, the more data we have, the better we can do. So we can share and combine our data to make a better, to make the best we can to detect this signal. This is just the sky map of the pulsars that we have in IPTA now. So it's order of 50 pulsars with a decent coverage of the sky. Of course, most of them, they are found in the direction of the galactic center. All right, so can you just tell me how much time do you expect me to talk so I know whether I have to skip something or not? It's like 10, 15 minutes more?
20.
20, beautiful. Okay, let me spend maybe a second also talking about this. So the good thing about besides detecting the signal is that with that signal, you can also do astrophysics. So this f to the minus 2/3 that I showed you before is just for a population of circular gravitational wave driven binaries, right? However, first of all, the amplitude of this signal here depends on the population of massive black holes. So it depends on the merger rate of these black holes and depend on their masses. So from the amplitude of the signal, you can say something about this population. Moreover, if the signal is not driven by gravity, if the binaries are not driven by gravitational waves, but they're driven by the environment, then what happens is that the shape of this signal at low frequency changes. Okay, so perhaps it's not an f to the minus 2/3 power law, but it can become flatter. Okay, and so perhaps instead of having an f to the minus 2/3 power law like here, if you have, for example, a population of stellar-driven binaries, you have a flattening at low frequency. So perhaps, in the future, if you have a detection and we can probe the spectrum, we can derive information about whether those binaries are driven by stars and gas, whether they are eccentric or not, and so on and so forth. Okay. Where are we at? So I had some fun last year putting together these plots. So essentially what you see here, these colors are essentially predictions that I found in the literature, dating back as much as 1995. And each arrow pointing down is an upper limit that has been published by different pulsar timing arrays. So you see we are hitting 10 to the minus 15, which is where most of these models predict we should be able to see something, okay? So the current upper limit, most stringent one that has been published so far is the Shannon et al. 2015, and it goes to 10 to the minus 15. Okay, so we are getting into the interesting regime, but we're not, the fact that we haven't detected the signal perhaps doesn't rule out much of the, let's say, allowed parameter space from what we know theoretically. Let me show you an example. So this is from Lentati et al. 2015, which is the latest published limit from the European pulsar timing array. So those limit, by the way, that limit wasn't super stringent. It was about 310 to the minus 15. So this is a limit on the A that I showed you before. You remember A times f to the minus 2/3, okay? So this is the amplitude of the signal at a nominal frequency of 1/1 year. So we took the best 6 pulsars that we had in EPTA, and what you see here are these Ellingson and Downs cross-correlation coefficient. And you see that they are perfectly consistent with the Ellingson and Downs, and they're perfectly consistent with 0, okay? So this is a non-detection. And what you can do, in this case, you can place an upper limit on the signal, which for this data set was 3 times 10 to the minus 15. Okay, so this is just subsequent work from some of my collaborators just showing with population models that even the most stringent upper limit that we had at the time, which is this 10 to the minus 15, it's starting to place constraints on the supermassive black hole binary population, but not super stringent. So for example, here, you see in the most optimistic model that we have, like in the top right panel, the white region here is the prior in the distribution. The blue region is the posterior given this upper limit. You see, you just modify the prior quite a bit, but you don't rule out the model. Okay, so those limits are sort of stranger than becoming interesting, but they don't allow us to do much physics yet. So let me just take another minute to say something different. So I show you this f to the minus 2/3 power law, but I also show you that the signal might be dominated by few individual sources. And depending on the model, since we don't know exactly how the population of supermassive black hole binary looks like, depending on this population, if you take different models, you might have a particular population where you have actually an heavy domination from these individual black hole binaries. So it's also useful to develop algorithms that that are sensitive not to a stochastic background, but to bright individual sources. You do the same, you put now a deterministic model describing essentially a sinusoidal wave in your timing residual, and you look for this signal into your data. Again, this is an example of such an analysis. And what you can do, if you don't have any evidence for a signal, you can place an amplitude of or you can place a limit on the amplitude of these individuals. And when you place this upper limit, you can actually rule out the existence of binaries in the nearby universe. So for example, the current upper limit of, let's say, 10 to the minus 14 around 10 nanohertz here that was placed by this European pulsar timing array collaboration paper, can rule out, for example, black hole of 10 to the 9, few 10 to the 9 solar masses out to comma and beyond, okay? Which is not very stringent, because if you take a typical cosmic population, you don't really expect, you expect, you have a little chance to have a binary, such a compact massive binary in the nearby universe. Okay, let me skip this. And let me dive into the last 10 minutes of this talk, which are going to be the most exciting, I anticipate. Now, let's look at this plot once again. One thing that you can notice here is that upper limits have been going down for quite a while with this Moore's law, if you want. But here they start to become sort of steady, okay? They don't really get down that much. And in particular, a reanalysis of many of those data sets with updated models and including more physics and things that we learned in time, essentially indicate that those upper limits are not as stringent as we thought before. And there are several reasons for this. So let's take, for example, this one, which is the Shannon et al. 2015. The Shannon et al. 2015 was essentially a single pulsar limit. So they had 4 millisecond pulsars, but of those millisecond pulsars, 1909, which is possibly the best pulsar in the universe, at least that we know, to make for this business, was heavily dominating the capability of, the sensitivity of this small array. And what's the problem? The problem is that you have, pulsars do things, okay? And those things create intrinsic red noise in the pulsars. And what you have to do to detect the correlated red noise is to model together the intrinsic and the correlated red noise to see whether your data favor a correlated noise or a intrinsic noise in some individual pulsars. If you have only one pulsar effectively in your array, you can't do this distinction. And the risk is that you overfit the intrinsic red noise of the pulsar. So perhaps there is some red noise in the pulsar, you fit that noise, but some of it is actually coming from a cosmological signal, but you're just fitting it out because you can't cross-correlate this with other pulsars. Recent other limits, the subsequent limits from NANOGrav, had issues with the solar system ephemerides. And let me tell a second in words what this is. So when you measure the time of arrival of a pulse with your radio telescope, you have to refer that time of arrival to a common reference system. And this reference system is the solar system barycenter. Problem is that we know the solar system barycenter only to some degree of precision. And if you don't know exactly where Jupiter is or where Saturn is, you might make a mistake in the calculation of the solar system barycenter, which can be of several tens or hundreds of meters. Now you say, okay, several hundreds of meters doesn't sound that much. But actually you can see that with your timing residuals in your pulsars. So the thing is that this error in the measurement of the solar system ephemera, of the center, of the barycenter of the solar system, is going to show up as a correlated red noise in your pulsars. But this correlated red noise, if you think about it, doesn't have a quadrupolar pattern, but it has a dipolar pattern. However, if your measurement is marginal, it's essentially impossible to distinguish a dipolar from a quadrupolar correlation. So there has been a hint of some correlation in those data. And some of it was due, it has been shown that is due to errors in the measurement of the solar system ephemeris. Since 2015, moreover, there has been some evidence of some common red signal of unknown origin in several pulsar timing array data, okay? But the nature of this signal hasn't been assessed. So it is likely that there is something in the data, but since we are in this marginal situation where we might see some correlated signal and it's very hard to distinguish a quadrupolar from a dipolar from a monopolar correlation, okay, that signal has been overfit or had been absorbed in the solar system ephemeris scheme and so on and so forth, okay? But the thing is that for some reason in the past few years, we haven't been able to push down this limit. And this brings me to the paper that has been put together today on the archive from the NANOGrav collaboration. So this is an analysis of their 12.5 years dataset. And what you see here, so I show you a couple of key plots from this paper. So first of all, you see here essentially the power spectrum of whatever correlated red noise they detect in these 43 pulsars, using a scheme that accounts for solar system ephemeris and all other sources of noise. So they see a correlated red process in their lowest frequency beams. And those are these 2 points here, okay? So there is, it's beyond any doubt that there is some correlated signal in there, okay? What you see on the right is a plot of the amplitude of this correlation versus the slope, okay? So what you expect from a population of inspiraling circular supermassive black hole binaries, this f to the minus 2/3 in strain amplitude, and translates into 13/3 in this quantity here, okay? And is the black line here. So of course, this posterior is not stringent at all, but is not inconsistent with it. So if this is in fact a gravitational wave signal, the amplitude would be 2 times 10 to the minus 15. Okay, this A here, which is.
So what are the different colors there?
Different colors are from different analysis. So let me explain a second that. So when you study this red noise, you can try fit this red noise with as many beams as you want, okay? So if you include 30 beams in your fitting, you see there are these here at high frequency that actually want this fit to be flatter. And this gives you the green posterior, okay? However, you expect the gravitational wave signal really to dominate in the lowest frequency beam. So if you if you say, okay, I don't care about these 2 points, let me just see what is in the lowest frequencies, what you get are the blue or orange lines, which are essentially 2 different models. It's a broken power law or just a power law with the lowest 2 frequency beams. And this gives you an idea that the very, the lowest 2, 3 frequency beams are really dominated by a very steep red noise. Okay, so these are, different detailed analysis. I mean, just to be clear, I'm not presenting this as a detection. I'm presenting this as an interesting feature in the signal that, depending on how you do the analysis, it has different properties. But certainly there is some type of correlated red noise in there. And if this correlated red noise is a gravitational wave background, the amplitude would be essentially of the order of those upper limits that we've been putting for a few years that somehow we aren't able to make.
Say correlated, you mean common to all of them?
Common, yeah. Well, yes, it is common. Sorry, it is common red noise. And yeah, sorry. Let me take it back.
Not correlated in the sky.
It's a common red noise. Now, let me go to the next slide. You can actually look at how this common red noise is correlated. And this brings me to the next key plot that is in this paper. And so you see this correlation plot that I showed you before. The blue to guide the eyes is the Ellings and Downs correlation, and the orange is a monopolar correlation. Okay, so you see that, there isn't any strong evidence that this correlation follows an Ellings and Downs curve. So there are a few points here that are negative, but obviously the error bars are large. And in fact, I didn't report numbers here, but you find them in the paper. They have quite substantial evidence that this correlation is neither monopolar nor dipolar, but they really don't have any evidence that this correlation follows an Ellings and Downs pattern. Okay, so that's why I'm saying there is an interesting common red process in the signal, which doesn't have a correlation that you expect from a monopole or a dipole, which are the easy, let's say the most studied spurious signals that you might expect for a correlated red noise. The dipole comes from a solar system ephemeridis errors, and the monopole would come if you have an error in your clocks. If you have an error in your clocks, this would affect your timing residual in the same way, independent on the angle between the pulsar, and would give you this flat correlation curve. So it doesn't appear to be monopolar nor dipolar. There isn't any substantial evidence this is quadrupolar, but it's certainly interesting because as I said, this is some sort of common red process that have been present in our data for quite some time. Okay. So I think, this is prompting, of course, a lot of interest in the pulsar timing community, and all the pulsar timing arrays and the international pulsar timing arrays is actually working to, collect data, understand better what this common red process is, and to see whether we can actually, put together some real evidence that there is any correlation resembling of an Ellings and Downs curve. But we are not there yet. But this is certainly a very, very interesting result that has been put together today on the archive. Well, looking at the future, just to finish off, we have Meerkat that started operation in South Africa, and this is very, very important because it's going to give us a factor 5 improvement in the timing precision of all pulsars in the southern hemisphere. So this will really be a game changer in the way we can do timing of pulsars. Obviously, there is also FAST in China, the biggest radio telescope in the universe, which is starting to discover new millisecond pulsars in the northern hemisphere. And eventually, we will have the square kilometer array, which will allow us to make like a 10-fold improvement into our sensitivity. So don't look at this plot. This actually doesn't have to do with SKA, but we will be able to get down to 10 to the minus 15 or so. So with the SKA, if the signal is there, we will be able to really probe its spectral shape, perhaps localize identify individual supermassive black hole binaries, and really do, you know, very interesting breakthrough in new science in the forthcoming years. All right, so let me just leave you with my summary. So massive black hole binaries are expected to be the loudest gravitational wave in the universe, and precise timing of ultra-stable millisecond pulsars, of an array of ultra-stable millisecond pulsars, provides an effective way to probe this signal, okay? And currently, we are in the situation where there is some interesting common red noise in our pulsars. We don't know what the nature of this common red noise is, but instead, this is telling us that perhaps the recent upper limits that have been, you know, the most recent upper limits have been a little bit over optimistic, in a sense that, you know, we didn't take into account properly for some of this common red noise in the data. And there is a likely presence of this common red noise. And, you know, in the, let's say in a time scale of a year or so, we will really have much more people looking into it and more data coming. And this will really tell us what is the nature of this signal. It might really be that, you know, we're just screwing up again the ephemeris and that's it, you know. But at this time, at this moment, we cannot rule out that what we are seeing is a, you know, is a first hint of a gravitational wave signal from a supermassive black hole binary population. And with that teasing sentence, I'll stop and I'll take a question if there is any. Thanks.
Thanks a lot, Alberto. Very nice talk. Is there any question? Go ahead.
I have a question, Miguel. So Alberto, you showed the posteriors from NANOGrav. And if I understand that plot correctly, the peak of the posteriors is at a higher slope.
This one.
Than, so, yes. What could it be? So I have two questions here. So if you believe that the slope is larger than that of the gravitational wave background, could it be anything else? Because if I understand well your slides about the eccentricity and the environmental effects, they should lead to a lower slope, not a higher slope. And if you instead believe the 13/3 or whatever gamma is predicted for gravitational wave background, that would correspond to a very large signal, which seems to be inconsistent with most of the models that you showed in your historical reconstruction.
Yeah, okay. Before. So there's a lot of questions there. So the first question, it can be three things. So first, obviously, you see these points here, they have a large error. This is really marginal, right? So really, you know, it can still be consistent with.
So the slope you have on the left, is that the gravitational wave slope, the one you plot on the left, or is it the best fit?
The one that is plotted on the left, that's a good question. I presume it's the best fit. I had to look at the paper, but so it might be, you know, like the central point here. So suppose that this actually turns out to be steeper. So in my opinion, can be three things. First, it can be some other noise, and, you know, pulsars do, since they are all the same, intrinsically, they are possibly all the same type of object. They have some common instability that produce a steep red noise, okay? So that's why, you know, if you don't detect the Ellingson and Downs correlation, you're never sure what you're seeing. Second possibility is that it is a stochastic background, but from a population of cosmic superstrings, for example, which would produce a slope that is actually higher than what is predicted by supermassive black hole binary population. And third possibility, since here you see you have 2 points, is that the signal is very jagged because it's dominated by few supermassive black hole binaries. So it might well be that you have a bright system that is pushing up this low frequency point here. And, you know, since you're looking for a stochastic, since your analysis is looking for a stochastic background, it interprets that as a stochastic background with a steeper slope. But in fact, this signal is dominated by an individual source. So those are, at this point, I would say all possibilities are on the table. You know, either it's some sort of noise, or, you know, it's a signal of a different origin, or it is dominated by an individual source. And for the, and the other thing, in terms of astrophysics interpretation, I would say it is not really inconsistent. So here, 210 to the minus 15 would be here. Okay. So it's really, you know, it's marginally consistent with many models. And to add into this, I would say that many models in the latest years have been also driven by the upper limits that we have, right? Because when you put together so many of those models, for example, I take an example that I know because I wrote it, Sesana et al. 2016. So we tried to see whether including some prescription that was proposed by Shankar and collaborators into build the supermassive black hole population. This, you might have heard about this, you know, bias in the measurement of the supermassive black hole binaries that would facilitate, let's say, an agreement between the fact that you have these 10 to the minus 15 limits and, you know, the population of supermassive black hole binaries, and apparently it does so, okay? However, if I don't take that specific, you know, putative bias in the measurement of the supermassive black holes, I go back to, you know, my 2013 models, and they go up, you know, I would say almost comfortably to 2 times 10 to the minus 15. And
besides,
fact,
if I understand well, these are average predictions. They don't account for the presence of the lucky or unlucky case in which you're dominated by a single source. These are average.
Oh yes, yes. And plus, plus you have all the tails that are due potentially to individual sources and so on and so forth. And those are only the 90% confidence. So there are all these models have tails. Actually, I can also say incidentally, you know, around 2013, there was this revision of the massive black hole galaxy relations upwards, like, you know, from Corman and Hu, McConnell and Ma, etc. And back then, if I incorporated those corrections, let's say, to the typical signal that you get, you consistently get something which is between 1 and 2 10 to the minus 15. But then there was a problem that this was inconsistent with the limits. So, you know, the limits are uncertain, the theory is uncertain. So there is really room for this signal, if it's real, there is really room for being consistent with the cosmic population of massive planets, I would say.
Thank you. I have another question, but I don't want to be the only one asking questions. If others want to say or to pose a question, please go ahead. Maybe I will ask it. Well, there's a raised hand, yeah.
I have a hand up from Ricardo.
Yeah. Can you hear me well?
Yes.
Yeah.
Go ahead.
Okay. So first of all, thanks for the talk. So if you go back for a second to the plot with to the contour plot where you had the two binning approaches.
Where you have the two?
The two binning procedures when you reconstruct the NANOGrav paper.
This one.
The plot we were setting at, yes, that one. So on the right panel, I cannot really see. So are the green lines on the right panel a bimodal distribution, or is it just the tail of the?
It's just the tail. I mean, this is the central, you see the central, I don't know if this is 1 sigma or whatever, 68%. And then you see the larger contour, which has these tail here. But yeah, I think it's just the tail. I don't really by modality here. Okay. I mean, there is no, the other contour that you see here are just blue and orange. So this, you know, their green doesn't overlay to those here. It's just these blobs that you see here.
Okay, and if I may have, I have another very short question.
Sure.
So you basically said that it's quite, so there are, monopole and dipole are not that, well, let me pose the question in a different way. How likely it is to describe this quadrupolar correlation via some astrophysical mechanism of those pulsars? So is it difficult to construct a model that produces those correlations within the astrophysics of the pulsar?
Wait, so you mean a quadrupolar correlation?
Yes.
I would argue no. So in fact, so the fact is that there is no evidence that this yet that this signal has a quadrupolar correlation, because if you do if you compute the Bayesian evidence of, common but uncorrelated versus quadrupolar correlation, you essentially get zero, okay? So there is no evidence yet that this is a quadrupolar correlation. If this turns out to be a quadrupolar correlation, man, people will really look into all possible sources of this type of correlation, but really on top of my head, I cannot think of anything of astrophysical origin, intrinsic pulsar of the noise that produce a correlation that has a quadrupolar pattern depending on where the pulsars are in the sky. I can't really think of anything that produces this quadrupolar pattern. And that's why, perhaps somebody will come up and say, no, come on, can be this. But
could it be dark matter? Could it be action like, well, not if it is quadrupolar, but I guess if it is monopolar, could it be this action like particle? There was a suggestion and also a paper by NANOGrav where they said it could be a Bose-Einstein condensate. There could be if you believe certain models of dark matter, there could be a Bose-Einstein condensate which would make the galaxy oscillate.
Yeah, but that would be a monopole, wouldn't be a quadrupole.
Yeah, no, absolutely, yeah. No, this was my question. In fact, the question I wanted to ask. Suppose it is a monopole. Have people looked at since NANOGrav had that old paper? Did they look at how consistent it would be with that scenario? I haven't looked at the paper.
Not to my knowledge, but I think they. No, not that I know. Okay. But I know. What they claim in this paper is that they disfavor a monopolar correlation, but obviously this is still very, very marginal. I would say all of this is marginal, but yeah.
Because the thing is, I'm not sure whether there would be a correlation in the sky position, because these dark matter models would have different pulsars if they are at different locations, would have a random phase with one another. So I'm not really sure that it would produce a correlation.
Yeah, perhaps it would produce simply a common
red noise.
Yeah, that I don't know.
I even wrote to Charlie asking him, but he never replied.
Yeah, I know. I had the same experience, but yeah, to go back to Ricardo's question, if this turns out to be a quadrupole, I think at least, unless somebody comes up with a strong argument why some other process would produce that, I would argue that people would endorse the fact that it's a gravitational wave signal. But there's no evidence yet.
Okay, thanks.
More questions? Enrico, more.
Question I wanted to ask was on the action-like particles.
Okay.
Okay. So I think there is a question. So thanks a lot, Alberto. Very nice talk. And
yeah, thank you for the invitation. It was nice. Thanks.
I'll invite you again when it is possible to do so.
Maybe I can stop sharing and see you. Okay. Yeah. Yeah. No. Thanks for the invitation. And yeah.